Okay, so welcome to another video. In this video I would want to keep it as short as possible. We're going to look at biasing techniques, do some LTspice, so biasing. Okay, so we first consider a case where we have a microphone and we connect the microphone to an amplifier. In this case we are using a BJT. Then our amplifier is connected to a speaker. Amp. Okay, so as we've already described or explained, the microphone can give signals up to plus 10 or minus 10 millivolt, a sinusoidal. As we've already explained why we are doing this in earlier videos. If you are not sure why we are doing this, you can check out the other videos in the channel. So the real issue here is when you connect the microphone directly to the base, then the signal or the voltage between the base and the emitter is not going to be up to the required voltage threshold for the base emitter junction to be forward biased. Remember, if you want to operate the BJT as an amplifier, we want it to be in the forward active region. In the forward active region, the base emitter junction is supposed to be forward biased, and then the collector base junction is supposed to be reverse biased. So our microphone's 10 millivolts is not enough to do that. So we need, so let's see what happens assuming I put, so back to LTspice. So the components, I choose my transistor, and as usual I use the 2N2222 transistor because it's very easy to come by. Okay, so I press V and model the microphone as a voltage source, which is giving a sinusoidal output. So the amplitude is 10 millivolts and the frequency is 1 kilohertz. Okay, so just as we've been doing the collector resistor, I use 1K for easy calculations. Then I place my VCC right here. I'm going to ground my emitter and I'll ground my VCC as well. So everything looks fine. Let me choose 5 volts for VCC. So I'm going to wire everything up. By pressing W on my keyboard. This works as well. So I have to place the ground here to ground the microphone. So I know the voltage coming from the microphone is the base emitter voltage. So connected to the base and grounded just like the emitter 2 is grounded. Okay, so that looks fine. So now let's power it up and see what happens. When I try to run my simulation for 10 milliseconds, okay, so this is the input as we expected, but the output, let me move this up to get some more room. Let me just delete it. Okay, so change that to 1K. Alright, it looks like okay, so it looks like I'm getting something, but let me take away the add trace so that I really see what is coming out. What I'm going to do is the node voltage. Let me look at the node voltage here. This is node 3. So for node 3, what I'm going to do is so add trace, then I do V into bracket N for node 0, 0, 3 minus the center voltage, which is 4.44 volts. Okay. So I'm going to delete this node 3. Okay. So what I'm getting is what? Okay, so this is what I have here. Obviously, I'm even surprised I'm getting little amplification. Not even supposed to be. Okay, so let me go and study my circuit again. Okay, just hope that's not the one. Can see. Let me delete this. Rerun it. 10M. Okay, so now that makes a lot of sense now. So delete this trace and right click, delete this trace. So let's rerun everything all over again. So the first pin, I want to see my input, then the second pin, I want to see my output. Okay, so it's not looking good. So obviously this explains that the transistor is not biased. But if I put a voltage source in between them, you can press Ctrl and R to rotate, and this is 650 millivolts. Okay, so now there's some form of amplification, and I can clearly see if I change the trace and I subtract the bias output. That's so even if there's no signal, the output is resting on 4.1 volts. So I want to see without the resting point what really happened. So you can see there's really good amplification. So my signal of 10 millivolts has been amplified to almost times 35. So the issue is, how do I get rid of this extra voltage source to get a voltage around 66.5 and use the same voltage source as the VCC. So I'm going to delete this, wire them together, and I'll put a resistor here. Okay, so what is the value of the resistor that I'm supposed to use? For now, I'll just play around it and see. Okay, so I'll start with 1 kilo and see what happens. Do I run? And obviously it didn't work out well, but it looks okay. I don't know what's happening, but this is not what I expected. And so let's see what is happening here. So number one, let me check the voltage at the point. So the voltage at this node is 0. So why is that voltage 0? So what is happening when the current drawn is coming in? The current has two paths to follow. Either to follow this path to bias the transistor as a base current, or it will go to the other side, which will be of no use to us. Now mind you, the transistor has a very huge input impedance, let's say about 10k thereof, and the source has very low input resistance, about 10 ohms. So the path that the current will follow will definitely be the path of this resistance. So that explains why my transistor is dead. But I can block the AC DC path to the left by putting a capacitor in between them. So for now, not paying attention to calculations, I just want to make sure that the capacitor is big enough to allow the AC to pass through as a short circuit and block the capacitor. If you were really building this, then the size of the capacitors will be important, because size matters when you are building a chip. Okay, so now let's rerun it and see what happens. So after I put the capacitor there, now what happens is that okay, so I'm going to just look at the node voltage and see. So still it's not working as expected, but let's take some readings and see what is the current flowing through R2. Now we expect that current to go through the transistor Q1. So R2 current, it's somehow 4.2 milli amps, and of course the microphone is also playing around it. So the current itself, the operating point current is around 2.4 microamps. So if I have 2.4 as the base current, then what it means is that the collector current is going to be 100 times 2.4, sorry, 4.2. I'm only assuming that the beta of Q1 is 100. Maybe you can look at the specifications and confirm. So beta is 200 here, so that makes it 200 times that. So the collector current is going to be to have 200 milli, so 8.4 milli 1 2, so it's going to be 840 milliamperes. If I multiply that by 1k, then the voltage drop across the resistor is going to be 840 volts, which is not possible because I don't have 840 volts. So the transistor is expected to fail. So if I read the output of the transistor, obviously I am getting a swing. So now let me remove the middle point and we see what's actually happening. The middle point itself is 18.45 millivolts, so 18.45 M. see if I can trace. Okay. Okay, so we have this, then I press OK. So now I see what's actually happening. What's actually happening is very small voltage swing in micro volts, which is not useful at all. So in that case, we know our method failed, and it failed one because the current through the resistor, which ended up being the collector current, was too high. Another thing we should also look at is in terms of input impedance. Now, why input impedance is very important for an amplifier. So I have my mic, let's say internal resistance of 100 ohms, and it goes into an amp which has an input impedance of 10 kilo ohms. Now if the microphone is giving 10 millivolts, how much of the 10 millivolts will be sensed by the amplifier? So you have to use voltage divider because these two are in series. So the 10 millivolts times 100k over 100k plus 100. In this case, you are getting almost the same 10 millivolts, so that is fine. But the moment I connect a 1 kilo ohm here, in small signal analysis, this is an AC ground, so this 1k and this 10k are in parallel. So I'm going to have this in parallel with 1k, this in parallel with 1k, and without doing the calculation, we know when you connect two resistances in parallel, the effective resistance should be less than any of them, so it can't be more than 1k. So the highest we can get is something approaching 1k. So even if it's 1k over 1k plus 100, which is 1.1k, times 10 millivolts, we see that the voltage sensed by the amplifier in this case will be very much reduced. So it's a bad thing. So now, for two reasons, I have to increase the value of the resistor R2, which is biased. So I can call that R2, which is serving as a biasing resistor. So even though at this point I have the node voltage, you can read the node voltage from down here. When I hover the mouse cursor, the probe on this point, it's 779, almost 780 millivolt. That is fine, but then the current that I'm getting from the collector as a result is too high. So my amplifier failed. So what I want to do is start from a point. Now, assuming I know my VCC is 5 volts and I want the headroom, if you've not watched the video on the headroom, you can do so. I want the headroom to be big enough, so I want the bias output voltage to be resting around 2.5. so if my RC is 1k, then if I can make my IC 2.5 milliamperes, then I will have the transistor resting on 2.5 even when there is no signal, so that when a signal comes in, there will be enough headroom for it to swing without any clipping. So in this design consideration, I have to set my R2 to get a value, and I know IB and IC are related this way. So if I want to get 2.5 milliamperes IC, then IB should be then IB should be no, that's not, sorry about that. So IB should be 2, how do I get 2.5 milli divided by 200 as the beta. I really wish the beta had been 100, would have made the calculation easier. By 1.25, then I go 1, 2, so 1, 2, and that is 0.0125 milliamperes. Okay, so what value of R2, which is the bias current over here, what value of R2 will set the IB, which is a current that will move here and pass here, to that value? So that is going to be a simple calculation that I'm going to do here. VCC divided by R2 should be equal to 0.0125 milli. Okay, so 5, which is a VCC, over 125 over 1, 2, 3, 4, 5, 6, 7. That's a lot of zeros. Okay, so over 10 raised to the power 7, so times 10 raised to the power 7. So 5 goes here, 25 I believe, and I will separate 100 from the 10 raised to the power 7, and I have 10 raised to the power 5 and 25, and here I should have 4. So 400 kilo ohms should do the trick. So I'm going to change the value of I2 to 400 kilo ohms and see what happens. 400k, and I'm going to run this. So first we are going to confirm 2 things. The bias point voltage VBE from down here is right now. So in case you didn't see that, VBE was 675 millivolts, and the current through this, so the current is now somewhere around 10.8 microamperes. We were expecting somewhere 12 microamperes, but that's fine because there are a lot of approximation or things that we might neglect, so practically that's fine. And we look at our, and we are getting very good swing. So let me take out the middle point swing and see the actual voltage swing and the gain that we are getting. So I'm going to subtract the 2.5, almost, is it? So the middle point is somewhere 2.7. Let me just assume 2.7. Yeah, so 2.807. So let me be precise, 2.807, 2.807. So when there is no signal for the microphone, the IC passing through this will let the voltage here rest at 2.807, and that can be seen down there. So the actual swing that I'm getting is 0.6, and then when so plus or minus 0.6, so that's input of 10 millivolts peak is giving me 600 millivolts at the swing. That means the gain is almost 60, and that's good. So right now this method looks good. But what is wrong with this method? The main issue with this method is the fact that it depends on beta and the transistor. The beta value is controlled by temperature. So as the device is operating and the temperature is rising, the beta value will be changing and might not get the exact beta value that we expected, especially if we are interested in a very precise calculation. So assuming the voltage tolerance of 2%, and that might also affect our gain. Okay, I think I was not supposed to bring the percent, just to let's see how that affects our gain. So we are not seeing it significantly, but assuming we needed a precise gain, that's another factor. But most importantly, we don't want everything to depend on beta, because what if all of a sudden the beta drops from 200 to 150 because of temperature? Okay, so we will end this video here, and in the next video we'll look at other methods that will improve upon this one to try and solve the drawback. So that will be the resistive bias. Part 2. Watch out. So please don't forget to subscribe to the channel. Bye bye.